Hey, welcome back to the Cycle World podcast. I'm Mark Hoyer, editor-in-chief. I'm with Kevin Cameron, our technical editor. This week's topic is fun with materials. What are motorcycles made of? It's been a long evolution, mostly metals, irons and so forth. We kind of want to go through like, how are they made? What are they made of? What were the advantages? What were the disadvantages? And we're going to do the whole menu of the motorcycle here. We're going inside the engine and frames and, everything that everything's made of. We might even talk about composites. I don't know. We're definitely going to talk a lot about metals today. Core audience, like, we love you guys. Thanks for being here. Materials, getting weird on materials. Let's get molecular, Kevin. It's your job.
That's the job. Well, the motorcycle, of course, was basically a Starley safety bicycle with one of the Dion Bouton's little four-stroke engines mounted on it. And Georges Bouton was the Count's man. And he had these little motors running at 2,000 RPM before 1900. So they went everywhere throughout the world. They built 20,000 of them by 1900, and it made the motorcycle inevitable. And the bicycle craze hit in Europe in the 90s. No more penny farthing with the great tall
You mean
front
it's the
wheel.
1890s in case we're
Yes,
unclear.
the 1890s. Yes, for those of you who haven't been here very long, the thing is that everything came together to make the bicycle possible. The ball bearing, which reduced friction, the pneumatic tire, which reduced friction, the roller chain, which meant that your feet didn't have to spin at the same rate as the wheel, and seamless drawn steel tubing. Now, if you pedal a bicycle vigorously, you will feel it flexing. The metal parts are not yielding. They're moving in the elastic range, but they're accumulating fatigue cycles. And at each application of stress, there are some little relaxations, some little overstrained atomic bonds go pop, and over a period of time, cyclic stress can lead to cracking and failure.
You just reminded, as you've said in the past, everything reminds you of something else when you get to a certain age. There was a really great overhead shot from Tour de France a number of years ago, many years ago, 25, 30 years ago, where they would get the guys coming down the home stretch on the sprint to the finish. And they've got different specialists. Sometimes there's the sprinting guy, and I forget the guy's name, but he was an Italian with gigantic legs. And they had this overhead shot, and they ran it in slow motion. And this is the best bicycle in the world at the time. And this guy's got enough torque to be flexing the bike as the slow motion camera is going directly overhead, and you can plainly see everything whip-whapping out of alignment. It's beautiful.
Yeah. Well, the cheap way to make steel tubing is to start with steel sheet and roll it up into a tube and weld down the seam. But the problem is that a weld is a zone of weakness, not necessarily of strength weakness, but of fatigue weakness, because as the weld cools, it drives impurities toward the center. And that is subject to early fatigue failure. So there was money in developing a seamless drawn steel tube. And the Mannesmann brothers in Germany came up with this. It's anyone who's worked with clay will appreciate the Mannesmann process, which has a piercing function, and then these crossed rollers that have got the tubing between them They start out with a great big lump. And basically, what they're doing is they're causing a zone of tension at the center of this lump that allows the piercer to drive on through it. And of course, it's hot. So they were soon able to make long pieces of lovely seamless drawn steel tube. Name your wall thickness. We got it. And it was a big business, and it was necessary for the bicycle because of the aforementioned flexing that's going on constantly.
That would be what we call the DOM, drawn over mandrel, correct?
Drawn over mandrel is the seam welded stuff, yes. And then, of course, you have the problem of joining the tubes to make a frame. And the elegant way of the early days persists to the present moment in the form of those lovely filigreed lugs that almost look electroformed. They're so spare in their use of material. The tubes go in the spelter, the brazing compound, and then the thing can be heated to form the joint. And this is not welding, this is brazing. Well, mild steel tubing is one choice. And in the early years of the 20th century, there was so much metallurgical research going on because the Western world at that time was rapidly industrializing. Let's not leave out Japan. So there was a need for all kinds of different alloyed materials. So the place where these raised frames were weakest was at the junctions, because if you think of leverage applied to a frame trying to twist it, the greatest leverage is at the point of attachment, because a small force applied at the far end of the tube has great leverage over that attachment. So people hit upon the idea, the Reynolds Tube Company in England, who started out in the nail business, hit upon the idea of using something that looked a lot like Mannesmann's equipment for seamless tube drawing to form tubes that were thicker at the ends, where the stress is greater. Now, this is the absolute ideal of economic structure, is to put the material where the stress is, and rather than just say, well, 2x4s are what we got, so bam, bam, let's build a house. We're not trying to make lightweight houses that can blow away easier in a tornado. So, but on any kind of vehicle, we're looking for economical use of material. And the idea of making the tubes thicker at the ends, called butting, the Reynolds process came out in 1897. Now, we tend to think of 1897 as a time of people posing for 30 minutes for severe-looking portraits. Well, that's great-great-granddad right there. He was a right bastard. And he looks it, because he doesn't want to be there for half an hour like that. But all this wonderful work was going on. People were saying, what if we... And then they got busy and did it. So these butted tubes were made thicker on the end, and it was a complicated process that involved a mandrel inside the tube, which, when the butting process was finished, could not be removed without enlarging the tube enough to slide the mandrel out, and then they drew the tube back down to the original diameter. So it's like the steel was the modeling clay in your hands if you worked with modeling clay when you were a child. I certainly did.
Yeah, it's a reminder that this phrase "hard as steel" is not exactly accurate. I mean, it is hard, but it's also so fluid, and you can do a lot with it, especially with temperature.
It's malleable, yes.
Yeah. Double butting, triple butting. They were doing all of that. That was a big thing when before the composite craze took over in mountain bikes and so forth, 25, 30 years ago or more. You had mountain bike frames that were double butted tubes, but they put the butting on the outside so you could see it.
Well, yes, it's good. If you're going to sell somebody something, it's better if they can see what
It
it is.
looks, I could see the difference.
Look how
Okay.
cool this is. Um, anyway, the material itself was a question. Mild steel has its limits. So in 1935, Reynolds Tube came up with Reynolds 531, which was a manganese molybdenum steel. And when I saw manganese, I thought, oh, that's what they put into pneumatic chisel steel, jackhammer chisels. And the idea there was to maintain fine grain size, which is a bulwark against brittleness and cracking. And the manganese had acted like a magnet on carbon, which otherwise might segregate at the grain boundaries, leading to brittleness. And they sold the daylights out of that stuff. Max Norton chassis were made from Reynolds 531, and those of you who are old enough will remember Ken Sprayson, who joined Reynolds Tubes in 1950 and made a lifetime of making the most beautiful motorcycle chassis for demanding applications. So steel tubing is not just a piece of pipe, although in my mind I sometimes refer in a derogatory fashion to chassis of pipe, because that is certainly the past now, except for particular applications where steel tubing has advantages. Anyway, in the US, 4130, which is a chromium molybdenum alloy, it can be welded. 531 doesn't weld well. It's intended for brazing. Don't get it really hot, because its interior trickery doesn't function anymore then. So 4130 was developed for the aircraft industry. You see those giant radial engines on a DC-7. They're supported by this spindly little structure of 4130 tubing, which is like, 2¼ inch stuff, attached to a ring that then bolts onto the back of the engine in numerous places.
Chromoly. We always call it
Yes,
chromoly. Kevin
chromoly.
said it, but it's chromoly. It's chromoly. Yeah.
So lots and lots of motorcycle frames have been made from 4130. And there's the image in my mind. Irv Kanemoto, famous tuner, engineer, worked with Freddie Spencer. He decided at one point that he wanted to try a stiffer chassis for the KR750 Kawasaki Triple, liquid cooled, vibrated tremendously. So he goes to C&J and he says, I want the frame to be made out of this 1 3/8 stuff. Well, that troubled the people greatly. Well, there's got to be a reason why everybody uses 1 1/8, 1 1/16. I want 1 3/8. So eventually he did get a frame made like that. And of course, the stiffness of tubes rises as a tremendous power of the diameter. So the thing was hell for stiff. But right about that time, along came long travel suspension, which reduced the load of the suspension on the chassis And so spindly little chassis like that of the TZ750 could survive in that world just fine. Crazy stuff. Anyway, the Manx Norton chassis was made of Reynolds 531 tubing by low temperature brazing, and it was a very influential design. Twin loop broadly supported the swing arm between the two loops at the rear. It was a little weak around the steering head, people tell me, who are running them in vintage. But it looks like it would be. During hard braking, there's no diagonal member from the top of the steering head to a firm point located farther back. But people tried in the 1930s to make aluminum frames. It was a French outfit with a wonderfully unpronounceable name that I won't attempt to reproduce. But they, again and again, they cast this frame in aluminum, and it was going to be the gas tank and the chassis. And this puts me in mind of so many people I knew when I was in my 20s and 30s who were going to revolutionize the motorcycle by radically combining the functions, several functions into one part, which is a noble goal. Not so easily achieved because they poured the gasoline in and it ran out through numerous porosities. And when repeating the pouring process under different conditions didn't improve matters, they finally just gave a wonderful Gallic shrug and applied a sealer to the inside of the tank, but it didn't go anywhere. So,
well, it's the same thing happened with the British engine cases you would read in manuals of the day, where and transmission cases, if it's you couldn't figure out where the leak was coming from, it was possibly coming through the material itself, through the porosity of the casting. And the fix, as described in many books, was to take everything apart and take the engine case where you suspected it to be leaking and peen it. Take the peening end of a hammer and just tut, 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 and smash all that stuff together.
compress the surface, yes.
Let's just say we have it pretty good these days.
We do indeed. Multaco had that in their if this happens, do this section. So in 1968, OSA produced a welded monocoque chassis for their 250 single-cylinder disc valve two-stroke, ridden by Santiago Herrero, a brilliant Spanish rider, and it was a strong performer and weighed very little. The next that I actually personally encountered was when Eric Offenstadt, a car and motorcycle sort of revolutionary, would-be revolutionary. He wanted to build all kinds of things. Instead of rattling on about it on the internet, which did not then exist, he built it. So he built this welded monocoque chassis for the severely vibrating Kawasaki H2 engine. It's an inline triple, and it does this when it's running. And so the aluminum did that. And every night they would load up and go to the welder during Daytona practice. So that wasn't happening. Then the next biggie, by an industrial corporation, Yamaha Motor, who had R&D clout. In 1980, they decided we will now build square tube aluminum chassis for our 500 inline 4 Grand Prix bike. And Kenny Roberts related that the thing would crack every time they took it out to run. And since they were based in Holland, that wasn't necessarily very often because there's rain associated with the North Sea. But gradually, they just kept building frames. Okay, we'll make the wall thickness greater. Oh, it's cracking at the joints. Maybe we should make them more organic, more flowing. Let us now be inspired by the roots of a tree. And it worked. They didn't look back. They made first the square tube aluminum chassis, which was welded out of a material called Z5D. And a friend who had access to some military information pool was able to get me the composition of the material. Oh, very hush hush. It turns out that it was developed for making freight cars out of aluminum. And its benefit was it did not require post-weld heat treatment because it was a precipitation hardening, age hardening alloy. Now, the thing about 6061 is that it does require post-weld heat treatment if you want best quality. And to prevent the thing from sagging in the oven, you've got to build this structure, a kind of scaffolding around the frame to guarantee the accuracy of the steering head with respect to the swing arm pivot. So that square tube aluminum chassis evolved with the help of, what is his name? The Spanish constructor, Cobas. He was building chassis that were designed for engine service. So there were two beams from the steering head that went to the back of the engine and gearbox unit and then turned downward to form what you might call swing arm uprights, because the swing arm was carried between those uprights. Now, these large beams were fabricated from aluminum sheet by welding. So suddenly racing motorcycle frames changed. The uprights were machined from solid, the steering head was machined from solid, and then they were joined together by formed sheet metal beams. And the perimeter frame that Yamaha talked about in their promotion for such a long time originated at this time. Kawasaki, on the other hand, had built a riveted, was it riveted? I'm not sure. But at any rate, a box section aluminum chassis for their 500cc disc valve square 4 GP engine.
I have seen a riveted version.
Yeah. And of course, when you weld aluminum, you take a chance. When you rivet it, the material is not heated. So if you use standard riveted joint design guidelines, you should have something good.
Well, when they were using aluminum in aircraft in the early days, they were welding joints, and they gave that mostly up for structural applications, welding, because it showed a lot more cracking than a riveted construction.
The big exception now was the wing carry-through structure of F-111, which supposedly was diffusion bonded. This is really crazy because it basically says if you put these pieces together under some pressure and elevate the temperature and just wait a while, the diffusion of atoms goes on constantly. And eventually it all becomes wonderfully solid without having to be raised up to melting fusion temperature. Bold project.
Yeah, gosh.
Swing wings, diffusion bonded carry-through structure. Wahoo, as my friend Ron Burns would say. Anyway, the Kawasaki impeded engine service because the one thing that you do with the two-strokes, you have the spark plugs out every practice. Sometimes you have the heads off every practice because you want to know how the piston is doing, all of them. So what soon became one of the dominant forms of the modern motorcycle was this twin beam thing that is open in between. Oh, I can reach right in there and remove the carburetors, fuel injection, throttle bodies, what have you. It was a frame that mostly stood to one side while you did your work. And of course, Tamburini at Ducati designed their trellis frame, which in its wonderful flexibility, and when you look at how it's made, it looks as though he was actually thinking, I can let the steering head move from side to side without tilting. But of course, we can only speculate as to what went on in his mind because he's no longer with us. But a brilliant designer who started out without all of the preconceptions that we gain through higher education. So those have been the major forms of motorcycle chassis: the twin beam aluminum frame and the trellis steel tube frame. KTM became a leading advocate. Ducati had to abandon the trellis frame for high performance models around 2000 when they found that the trellis was no longer stiff enough to deal with tire grip, which is constantly. Dick O'Brien had some salty words for the people at Goodyear. He said, just when we get our chassis working great, here those guys come, and he characterized them. here they come with more grip, and all our work is down the drain, and we have to do it all over again. Well, that's how motorcycles advance. The tire people come up with more grip, with more desirable properties. The chassis was designed for some other combination of properties. Oh, all right.
Well, that two famous moments in Supersport when the a new grippy tire came out. I think it was the D207 Dunlop RR, and they were testing, and they said we're getting chatter, and engineers said, "Well, go back to the old tire." That was their solution for getting rid of the chatter. And then I think you shared with me the switch to wire spoke, laced wheels, and because they have a little give, the chatter frequency was moved away and the chatter was eliminated. So
the race team said, "Why can't we issue a heritage model,
heritage edition
with
600?"
Yeah, everything about those 600 was, as radical as you could make on a production line, and put wire wheels on it. No, we're not doing that. So, okay, we've dealt with this type of metal chassis structure. All the while, there are people trying to make carbon fiber reinforced plastic chassis. And at the time, the objection to the carbon fiber was, well, yes, we know that it's wonderfully light, it's wonderfully stiff, but can you repair it? Or if the tire companies do come with more grip, can you alter it? Well, no, we actually can't. Well, then we're not interested. But it's always been known that these properties could raise the game. So what we see now is carbon fiber swing arms sometimes, which we're told allow more flexure without cracking. So the notion that when you're leaned over, that the rear suspension with the shock absorber and the linkage is nearly at right angles to the bump action, which is straight up and down, whereas the flexibility, the lateral flexibility of the swing arm beams becomes the suspension. So hence the current interest in carbon fiber swing arms, which can move laterally more while remaining reliably strong and sound.
Well, you saw that evolution with aluminum swing arms in superbike days, where you used to have a pretty wide beam, and then you had a bracing structure welded to it over, and sometimes it was sheeted in, but it was quite wide. And then we saw the evolution to where the swing arm legs going around the wheel were quite thin.
25 millimeters.
Yep. And then vertically, everything was, built up massively.
Yeah, to resist axle
bending.
twisting.
Yeah.
You want to keep the two wheels parallel to the same
Right.
plane. They may move from side to side.
Yeah.
Because, for example, when you lean over, the part of the tire that's running on the ground is not centered. So the motorcycle isn't objecting to that. So we can allow them to move laterally.
Well, there was I don't know if it was a coincident evolution, but certainly swing arm pivot. If you look on your RD 350, it's about as big as this Tombow pencil.
Oh,
and then the rear axle also as big as this Tombow pencil.
Solid.
But, solid.
Yeah.
And then now what we get are these beautiful materials, thin wall, large diameter, and that's to keep that structure strong so that you get basically it's a parallelogram.
Yeah. Yes,
So
and it's flexing as a parallelogram.
Yeah.
But of course it's a spring without a damper. And the nice thing about carbon fiber, which hasn't been mentioned, is that because the plastic is not infinitely rigid, it has some natural damping. They make bells out of metal because it keeps on ringing. A wooden bell, clunk. The faithful do not come for evening mass. So that's where frames are pretty much right now.
I've felt different damping in tires, by the way, just as long
absolutely.
As long as we're on the subject, changing the tire, changing the weave, changing the rubber, tires that are bouncier.
Yep.
To tires that do not do that, which is generally something I think better for me.
Yes, dropping a ball of putty on the floor versus a ping pong ball. Well, one of the things that has always greatly interested me is the actual hot parts of the internal combustion engine. And because I suspect the railroads had required such expertise to be developed in the casting of iron, that was a universal metal around 1900. There were lots of foundries that could cast it with great skill. So cylinder heads and cylinders were cast iron, and they could make them with fins, how many, how deep, you name it.
Didn't have to put seats in them either.
Yes. Yep. This was mentioned in the material describing Honda's Super Cub 50cc step through. Why did you make the cylinder head out of cast iron? Because we didn't have to have separate valve seat rings, didn't have to have separate guides, and a solid iron cylinder means no boring and fitting of a liner.
How inexpensive? How do we make it affordable? How do we make it affordable? And that's how you do it. Because if you get a beautiful cast aluminum cylinder head, it's transferring heat and it's got all these fins. You have to put hard things where the valves are closing. You have to take care of that, and it's a lot of extra work. It's worth it sometimes. But if you want something that just functions, if you want a motorcycle like the Super Cub, which we just did a podcast on a week or two ago, you just get rid of that. Ford 460, current reference for me. I've been inside a 460 for the past, it's running, but it was months of being inside of it. And
he's inside and he can't leave.
Yeah, God, it's nuts, going good. But there were no valve seats on that. That was all just their cylinder head. And when you get a crack on the seat area, you have to drop a seat in and then seal that crack using interesting pinning methods and stuff. Stitching of cast iron.
Yes. So Honda came out with the all iron head and cylinder in '58. In 1966, they switched to the higher conductivity aluminum. But here's the problem. You've built your iron engine. It has a modest compression ratio, and it doesn't put out a lot of power. And you're happy to go waffling along an English country lane at 35 miles an hour, enjoying the beautiful world in which we live.
Yeah, Ironhead 54 Triumph is a little bit quieter than the later alloy heads. They're really
Yeah,
nice.
yeah.
They don't have as much pop, but they have their positive qualities, but the envelope of performance is a little smaller.
Everything is designed to a set of conditions. So as the American market said, where's the beef? Come on now, where's the beef? So they're going to raise the compression. They're going to give us a little more valve timing. Oh, it's making more power. If it makes more power, it makes more heat. How does a constant number of fins get rid of more heat? By becoming hotter. So this means the cylinder head, in order to rid itself of the heat of higher performance, has to operate at a higher temperature, because what is important is the difference,
Differential.
the delta T between the hot thing that we want to cool and the cool medium to which we can transfer the heat. So eventually they said, okay, we're running into detonation here. Detonation, by the way, is not pre-ignition. Detonation occurs after a completely normal cycle. It's nearly burned out to the cylinder wall, and just as the flame arrives near the cylinder wall, sudden terrible spikes come up on the pressure volume diagram.
In a gasoline engine, the combustion is initiated by the spark, and then detonation happens.
Yes, later.
Pre-ignition happens before the spark, and it only happens very few times before it all goes wrong.
Punches it through.
Yeah, detonation can go on a little bit longer, but not that much longer.
Here's Harry Ricardo, a name that you've heard me go on about. Why doesn't he shut up about old Harry? But Ricardo was a wonderful combination of a curious person, a hardworking person, and he had a respect for money that resulted in many patents. So Harry says, let's try bronze. So on the Ricardo Triumph 500, they made the head out of bronze, and indeed it was an improvement in heat transfer, but not an enormous one. Yet the valves could still be seated against the bronze, and their stems could operate in guides that were integral with the casting. But the humans never stop. Once they find something that is rewarding, they just, like the people at the machines, they keep pulling the handle and putting in quarters. That's called R&D. Getting lucky
Really big
is another
coins.
matter. Yes. So compression ratio is rising. In the mid-20s, leaded gasoline arrived, which meant that its octane number, its resistance to detonation, could be raised arbitrarily, depending on how much of this extremely poisonous substance could be put into the fuel without causing spark plug problems. So engines are making more and more power. And again, we run into that system of, well, now in order to get rid of the heat, the head has to operate hotter. And now we're detonating again. You hear that little chittering noise that sometimes is audible to people who still have their hearing. And it was time for a new material. Well, let's make the heads out of aluminum. Sorry, guys, the hard seat rings that aluminum requires for the valves to seat upon, we can't keep them in the head. At the operating temperature of the head, the aluminum is already kind of losing strength. And So they screwed the seat rings in, they swedged them in, they shrunk them in, they all came loose.
Skulls. They use
Yep.
skulls. They use like little cast skulls of where
Yes.
the valve rings would be, and then inside
And
it
the
was meant
spark
to
plug threads.
spark plug threads, and it was meant to hold it all in there, and then they cast the aluminum around the skull.
The skull by itself looks like a weird pair of steampunk spectacles.
Yeah, with the cross eye mechanism in the middle.
Yes. And Norden, with their racing engines, persisted with skull construction until 1950. And the Horners in Australia have used skull construction on their Irving Vincents, the 4-valve ones, because it's so difficult in an air-cooled engine to avoid cracking between paired exhaust valves. The place in between the two very hot valves and ports, that metal is constantly being expanded and contracted. And when you do that with metal, all those little defects, all those little lifetime unions that suddenly go, you're losing bond strength, a crack forms, badness. In all sorts of high duty air cooled engines with aluminum heads, it is fiendish, the ingenuity of nature in thwarting your ability to make all of this work properly. But eventually, what happened was in the U.S. at McCook Field in Dayton, Ohio. Whenever I type Dayton, an A forms at the end of it. My fingers want to say Daytona. There is S.D. Heron, a crabby Englishman, who is deeply annoyed that everyone isn't as clever as he. And you've met these people.
I have.
Yes. He's annoyed because the seat rings won't stay in the air-cooled cylinder heads that he is working hard to develop for aircraft engines. And then he thinks to himself, wait a minute, didn't we do something like this in 1916 during the First World War? A material called Y alloy was developed that had outstanding hot strength, but it could only be forged. It couldn't be cast. If you cast it a little bit too cool, it wouldn't fill the mold details. If you cast it hot enough to flow and fill the mold perfectly, it bubbled up with porosity. It's Mother Nature at work. She's playing with us. And so he thought, okay, this is a U.S. Army facility. They have a staff metallurgist here. I'll go see him. So he goes to see E.H. Dix, D-I-X, Jr., who would later become chief metallurgist for Alcoa, an enormous corporation. But here he is at McCook Field, and Heron says, look, here's the problem. This material doesn't have, the material we're using doesn't have enough hot strength. Y alloy does, but we can't cast it. So can you doctor it, come up with some kind of a fix? And Dix goes away and does his magic. And the material that he came up with, alloy 242, I think, was used to cast millions of air-cooled radial aircraft engine cylinder heads during World War II. Millions. And it wasn't perfect. It wasn't easy. It was never easy to cast, but it was enough better to justify its use. So, as close as I can figure, somehow Velocet learned of the existence of this improved cylinder head material, and they adopted it and had superior head cooling, which meant they could run a little more compression than the corresponding 350 Norton Manx. And that persisted until 1950. But this is the kind of thing that happens.
I don't know, man. Knowing what I know about Velocet, I'm surprised they spent the money.
Yeah, well.
Gotta win.
Yeah. Unlike Norton, who, like all racers, spent. What do you mean? What did we spend? All we had.
Yep.
So um, it became possible to make seat rings stay in this new material. And when the late John Whitner, who built that marvelous modified Guzzi for Battle of the Twins racing that had the parallelogram rear arrangement so that it didn't climb and sink with the throttle, shaft drive model like BMW's. Uh, he was invited to come to the factory and work as an engineer, which he did for several years. And while he was there, he designed the 4-valve cylinder heads for that 90-degree V twin. And looking for the alloy, he said to me, I found the perfect material. The Italian alloy system is wonderfully cross-referenced. You sort of tell it what you're looking for, and it says, oh, well, it's got to be one of these. And he said, it wasn't easy to cast. And this would have been in the 1980s. So that material evolved over time to be just the ticket for air-cooled cylinder heads. But in pistons, Y alloy was steadily developed, or I should say, the alloying concept behind it was steadily evolved, which is the formation of intermetallic compounds, that is, bonds between different kinds of metal atoms to form hard particulates in the crystal lattice, which act as pins to prevent one layer of atoms from bump, 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 sliding across another layer. What results? Higher strength. If it can't slide, it can't bend. So this material was developed to the point in 1939 in the form of RR58. That piston material used for pistons, Ducati was using it for their race engines right up to 1999 or 2000.
Developed before World War II by Rolls-Royce.
Yep.
RR, Rolls-Royce.
Yep.
And they didn't call it just aluminum. They called it hyduminium.
Well, the hyduminium was the corporation that that sort of drove the development of aluminum metallurgy in England in a certain period. And the hyduminium guy was a Brooklands regular. So if you had troubles with aluminum material, they'd say, go see that guy.
Well, and he's out there directly suffering the problem because he wants something more, and that's where it comes from. Yep. I just gotta. But it's high. What is high durability aluminum? That's how they put it. That's how they got hyduminium. It's good stuff.
Yep. So today we have 2618, which is basically RR58, which traces its heritage back to 1916, and a steady development. Well, why aren't we all using high Zoot modern breakthrough materials? Because an old friend is irreplaceable. When you get an alloy whose behavior in being poured, in being forged, in service in a variety of applications, I think RR58 was selected for structural parts in Concorde because of its high strength at temperature. Concorde flew fast enough to have aerodynamic heating. So here's this material that's come down to us through the ages. Well, there are materials beyond this. At one point, Formula One began to play with what's called dispersed phase strengthening. I love this, dispersed phase strengthening. Now, if you precipitate the phase in the form of intermetallics out of molten material or hot material, that's legal according to the FIM. But if you add the hard particles to the aluminum and mix it in by repeatedly extruding it, that's a composite. Even though the strength generating mechanism is the same in both cases. Politics. Anyway, with this dispersed phase strengthening, they were able to double the strength of pistons versus 2618. And, you know, it's like this stuff is saying, to quote from the good book, all this will I give thee if thou wilt fall down and worship me. So that's where pistons are in terms of materials. In terms of design, we've talked about that so many times, you're probably sick of it. So early crankshafts. Motorcycles were built in small shops, not large factories. That meant that whatever you built had to be machinable on general purpose machine tools. So the crankshafts were made in 5 pieces, 2 cast iron flywheels, full circle, cored out sometimes to produce the degree of counterweighting, roughly speaking, which could then be corrected by drilling the rim of the wheels. 2 made shafts, steel, which were fitted into the flywheels by means of taper plus key plus a very thin nut for retention. And then the 5th part, the crank pin, which again was fitted into the flywheels by means of taper and nut. And I remember seeing a fellow who was known to his friends as Barry Badrist walking across a parking lot at MIT carrying a Manx crankshaft. And he was telling us all about how the nuts are tightened with a special spanner. And once they're tightened to the correct torque, the part that you engage the spanner with is sawn off to provide clearance for the connecting rod. Well, it wasn't long before the power-happy humans were not satisfied with 2,500 RPM. They wanted 5,000, 6,000, and so on. What was the result? The stronger steel material in the soft cast iron wallowed loose. So, okay, we'll switch to steel flywheels. And at this point, Robert Iannucci, always a driving force in U.S. motorcycle vintage racing and a controversial figure, steps in and says there are G50, matchless G50 flywheels, which are just mild steel, holding doors open all over the UK. Because the business of main shafts coming loose has to do with how strong is this material? What will it take to yield it? So others went forward with alloy steel flywheels and stuff that was all machine, no castings. High strength steels were not something that had to be invented by the motorcycle industry. They existed throughout British and American and German industry. Started out with, in the late 1890s, when someone discovered, I put 5% nickel into this heat of steel, and that stuff is strong. How strong? 40% for 5% nickel. I'm interested. Write it up. We can
You can
sell
see
this.
building, and people are getting thirsty. Building my Veloset engine, I bought some pretty high zoot valve springs, and you could see the sheen of really nice springs. These are expensive, high, they're way over spec'd, but I was so tired of breakages,
Yep.
around the whole engine. And man, just you can see the quality in the steel spring. It's got a sheen, it's got a little bit of straw color to it, and you just go, yeah, that's the stuff that's what I've been looking for. Yeah.
That's my stuff. Well, those fellows at S&W made a big breakthrough, um, I think in the 60s, when they said, let's try some wire made with this vacuum remelt process. That should increase its fatigue resistance. The problem with valve springs is, of course, that they are subjected to cyclic stress that is really brutal. And I remember Steve Scheibe, who was in charge of Harley's VR1000 Superbike project, saying, he said, there are crazies out there that are working their springs to 140,000 psi, and when you get up to a high percentage of the yield strength, where the metal stays bent after you remove the force, you're playing with, well, these springs will last a day. These springs will last one drag strip run. And of course, what happens after that is you have to search for a spring that cannot crack. And that is the appeal of pneumatic springs. There is no crack in the air. They do not fatigue and break. But anyway, those fellows at S&W started out with vacuum remelted steel wire, which was a German process from about 1957. Those people who have attended the higher technical universities in Germany work from first principles. So they look for what are the defects in this material and how did they get there? And of course, they're nearly always some form of oxide. There are various ways of removing that material, but there's always going to be crack nucleation, little entities in the material, and vacuum remelting sort of boils a lot of them away. Farewell. They go to the vacuum pump and are expelled into the atmosphere. So S&W Springs started with this wonderful wire, and then they shot peened it to place the surface in compression, because the highest stress in a valve spring is at the surface. So if you put the surface in compression, you can compress the spring a certain amount, and you have not increased the stress at the surface, you've decreased it. And that allows the rest of the valve lift to not work the spring as hard. This was the wonderful thing about shot peening. And of course, people shot peened rods. During the war, aircraft engines had beautifully polished connecting rods. The reason being that forcing some poor person to sit there and rub out surface defects meant that someone was studying and looking. Yes, indeed. This was how rods were made fatigue resistant before the onset of shot peening. And of course, the people, myself among them, who loved the appearance of polished steel connecting rods, thought that the dull sheen of shot peening, which was sort of like the surface of the moon, was disappointing. This other one over here, I like that one. Yes, but the performance is good.
Well, it reminds me also of the polished port versus satin port, and then you have those golf ball dimple guys out there, like
Yeah,
taking a ball mill and putting certain.
we had crankshaft failures in TZ750 in the flywheel disc that had two press fits in it. And as soon as we knew exactly where the problem was coming from, we would take the flywheel discs to the shot peening store and draw the man a diagram, and he would shot peen those areas selectively. And after that, we never had another failure of that kind. So it's real. It's not something that Madame will wear. Sometimes descriptions in hot rod magazines sound a bit like fashion reports. Down the runway came the stunning, etc. But in this case, it's not just a new fabric with an indescribable sheen. It is a functional necessity in valve springs. So onward and upward. Um, Connecting rods. The usual material for heavy duty steel connecting rods is 4340, or at least it's very common. And then along came Mar aging steel, which took over as connecting rod material. And then people like Jack Williams, 1953, he's head of racing at AJS and learning all kinds of stuff with very little equipment, mostly using his mind. And he learns of the existence of metallic titanium as a structural material, and he had to have some. He made connecting rods out of it, and it was wonderful. In the US, Bob Nichols introduced titanium rods to the Champ Car crew. And he described luncheons where there would be 4, 5, 6 people at a table, all of whom today are revered names in hot rod and Champ Car racing history. And oh, to be a fly on the wall, Bob Nichols was as close as I could come. But he introduced titanium rods to the Champ Car scene. And this was a great thing because it's somewhat lighter than steel. It has excellent strength properties when it's properly alloyed and heat treated. But it is not as stiff as steel. Strength and stiffness are different. If we take two rods of differing specifications, same diameter, put them into holes in a vertical concrete wall and start hanging weights on the end, the strength of the material is the point at which the weight is just big enough to yield the part. But the stiffness is the rate at which it bends per pound, the spring rate of the material. That is independent of the alloying content and heat treatment. So steel is at least twice as stiff as titanium. And in Formula One, they're finding that at 20,000 RPM, the titanium rod is sort of whispering to the piston rushing towards the cylinder head, please slow down. Oh, please. The rod's getting longer as the stress is getting greater. But we've cleverly provided enough squish clearance so that the piston stops short of the cylinder head contact and accelerates in the other direction. Now here's the rub. At mid-range RPM, there's too much squish clearance because the rod isn't being stretched as much. So now there's too much squish clearance. What do we do about pepping up of the mid-range? We go back to Mar aging steel. And metallurgy is just a service that's available in this world. You bring them your problems, and they'll get to work on the solution. Of course, you have to pay, but wonderful stuff. I'm always fascinated by. See, I'm nowhere compared with an actual metallurgist. Those people have the detailed knowledge that I wish I had, but I have just enough understanding. It's like as a small child lifting yourself up to the window edge and peering out. Oh, what realm is this?
Yeah.
So I am fascinated by the notion that manganese attracts carbon atoms, thereby preventing them from the deadly carbide formation, segregation at the intergranular zone. The manganese is nicely distributed. It's highly soluble in iron, and it carries those carbons away. Come with me now. Don't want to get in trouble, and prevents brittleness. So uh, let's talk about valves. Valves are the second hottest thing in the combustion chamber. The first hottest is the tip of the spark plug of the center wire, purposely made to be continuously above 600 degrees and below 1750. The exhaust valve is right up there. In early engines, they made the valves out of steel, and the hot exhaust gas containing reactive elements corroded the steel, causing it to lose its seal quite quickly. And in those early days, let's say it's 1906, and you're an extremely wealthy person, and you've bought one of the new motor cars. You've been told to hire a chauffeur. An agency sends over some fellows for your choice. Having picked one, you send him to the automobile manufacturer where he will be trained in how, every 6 weeks, to reseat the valves by grinding, how to change tires, how to change the oil, how to maintain the car. This is a lengthy school. That's how motoring was in the days when it was ruled by privilege. Now we have warranty. Anyway, people were fascinated by the new tool steels, which came out around 1900, which were able to cut steel at much higher speeds than carbon steel cutters. And there was some benefit in this. Tungsten steels for exhaust valves were better than mild steel, better than cast iron, which some people tried. Cast iron head, steel stem. There was one wacky idea that was tried. I think it was Frederick Lanchester, who created a diverter valve so that the same valve could function as intake and exhaust, but alternately. So it would be cooled by the intake when it was functioning as the intake valve, then heated by the exhaust during the exhaust stroke. It proved not to be necessary because around the early 1920s, people came up with the idea of self-protecting, aka stainless steels. Chromium forms a hard ceramic coating when exposed to air. So you may have seen on kitchenware the notation 18-8 stainless. That's food service stainless. 18% chromium, 8% nickel. Made wonderful exhaust valves. S.D. Heron commented on using tungsten steel exhaust valves in engines that were running the new anti-knock tetraethyl lead. He said the exhaust valves looked as if they had been dipped in liquid slag. They were useless with that type of fuel. But the stainless valves lived. And as time passed, of course, along came the gas turbine, and the British alloy Mnemonic 80A was quite successful in the hot sections of their jet engines. And when the war ended and all of these things could be talked about publicly, here came BSA saying, our 500 Gold Star has severe exhaust valve problems, a great big exhaust valve in a huge cylinder. And Norton at one point had to tried to cool the exhaust valve stem by circulating oil down a spiral passage next to the valve stem in the guide. And there was a little radiator on one of the frame down tubes for this circulation. So it was a severe problem in big
Sounds
cylinders.
like a recipe for coking is what it sounds like.
Well, coking would be tempting because running rich is a way to cool the exhaust valves. But what happened then was, of course, the whole jet engine thing was heavily backed by national governments, the factory team in the sky, so to speak. And a rash of superior exhaust valve steels became available. The British went with cobalt, the Americans went with nickel. And then the great thing happened. 4 valves per cylinder. Suddenly exhaust valves went from being 1.5 inches down to just little tiny sizes that were easier to cool. Second thing that happened, Honda liquid cooled the Goldwing 75, 76. It proved to be contagious because it solved so many problems. Today, nobody says, oh, exhaust valves went in my bike. No, the exhaust valves run for thousands and thousands of miles and never give any trouble because the material is adequately good, the cooling is wonderful, no problem. So we have arrived in that sense. What do we got?
I think we're good. I think we have one more section. It was wheels, but I think we'll just talk about the invention of the wheel on a podcast sometime, and we can start way back, and we can get all that old stuff in there. It'll be great. Well, that's it, folks. Yeah, I mean, you take your choice. You can go find your metallurgists and take them your problems and your money. And you can start to work on your specific issues. Just talk it through with them and make up the recipe. We have all benefited, and we've benefited on the vintage side where you've taken all these wonderful G50s and Norton Manxes and everything else, and they are being made with modern materials, and they're better. You can go to a fella in England, KTT, the Thurston Enterprise, and you can get brand new crankshafts made out of inviolable materials. Yep, crankcases that are beautiful.
They look glorious. They're just
and
wonderful.
Strong. None of this pouring into a mold and hoping that the porosity is low enough and making castings so thick because they're going to have some weaknesses, and we don't have to deal with that anymore. We get, as I am often fond of saying, you can buy a new sport bike, you can buy a new Ducati, V4S, you can buy a Yamaha R1, etc. Pick your brand. It kind of doesn't matter. Go to the dealership, get your 600-mile service or whatever it is done, then turn on that motorcycle and start lapping a track forever.
Yeah.
Tires go off, pull it in, change the tires, check the chain, check your wear parts, change your oils, and you just go on and on and on and on. Let it idle.
Because they're designed for that duty.
Let it idle for the next 2 years. Just keep putting gas in it. It'll do that. It won't overheat. It won't do anything bad. It'll just sit there and go, bah, and away it goes. So it's
And that's an achievement, because a lot of these things were touch and go in the 1920s. Um, in the middle 20s, the auto industry learned how to make press formed sheet steel structures with quite complicated shapes. And people looked at that. Motorcycle gas tanks at that time were folded out of flat sheet that had been primed with a lead tin alloy so they could be soldered. The joints were soldered together. Imagine putting a soldered together flat sided gas tank between the two top frame rails of your 1922 motorbike, long and low. That's how they liked them back then. And having this engine that is straining to get out of its mounts because it has been given more and more power. And now that poor thing made of flat sheets, it's vibrating in 100 different modes, and the solder is going, oh, I don't think I could do this anymore. Gas pours out onto the hot engine. Hurrah! So press-formed steel gas tanks that fitted down over the frame. People didn't like them. The old-timers said that they looked like apples split and jammed onto the chassis. It's hard being an old-timer because the world goes on by and you're still sitting there in the years of your youth. At least it happens to some of us. But all this stuff, every part on your motorcycle has a story. It has a history that can be discovered. Now, the healthy thing is to say, well, when I'm old, I'll read about that. Right now, I want to ride. Off you go.
Fair enough. Off I go.
Yep.
Thanks for listening, folks. Appreciate it. We'll see you down in the comments. Hit your like and comment. Share it with friends that you think might like it. We'd appreciate it. We want to spread the molecular word about motorcycling and get down in there. We'll go shopping for another whole motorcycle topic. So if you got an idea for a podcast on an epic motorcycle of our past or near past, get in the comments and let us know. Thanks for listening. Thanks for hanging with us over another Cycle World podcast. Take care.